Welcome to another episode of Calculus with Dr. Jed. This section, 6.2, is on volume. We're going to use integrals to find volume. Now in chapter 5, we use integrals to find area. The difference here, and here's the idea, is that the function we put inside the integral doesn't have to be the same dimensions as this. If this is an area, and we multiply by a distance, area times distance will give us a volume. Now the trick here is that we're going to multiply and the area can change each time. That may sound confusing, but the trick is that as long as we have one direction that we can measure everything about very effectively, this technique of finding volume works very well. Now I've got some examples to show that'll hopefully clarify. The first one is a classic example. We're going to build a pyramid. So the pyramid looks like this. It's a square pyramid. I'm going to say, just for argument's sake, the base is 200 feet on each side. The height is 100 feet on each side. So look at that. We've got 200 feet each way here, and that's 100. The question is, how much volume is that? Well, it's less than a cube, 200, 200, 200, or even 100 up that way. But how much less, and how do you figure it out? The trick is, if we can find a cross-section and measure it effectively based on the one good dimension, then it's an easy integral. So our dimension is going to be up and down. That's supposed to go in the center here. Pretend that's in the center. So, if we start at the top and call that 0, go all the way down to 100 down here, we'll notice that each of the little cross sections, if you just take a knife and cut through the pyramid, if it's made out of stone, you can't use a knife, obviously. So maybe a laser, I don't care. Whatever. If you cut that way, you're going to get a cross section like this. Now the height will be a little tiny a measure. We'll call that our dx. The area, what is the area? Well, it's a square. So the area is going to be whatever this width is and square it. What is that width? At the top, the width, which doesn't even really make sense, is 0. At the bottom, the width is 200. So at the top, the width is 0. At the bottom, when x is 100, the width is 200. That's not enough information yet, but the trick is that we can notice the lines on each side. It grows like lines. If it's linear, then its width is going to be a multiple of x. Look at that. 200 when it's 100. The multiple is 2. So our width is 2x. If our width is 2x, the area then is the width squared. 2x times 2x, which is 4x squared. So now we know it goes from 0 to 100. Plug those into our integral. 0 to 100 here, ax dx. Plug the 4x squared in here and integrate. Now if you recall, integrating a 4x squared, the 4 doesn't matter, we keep the 4 as a multiple. The x squared becomes 1/3 x cubed. Remember your integration techniques. And so we have 4/3 x cubed going from 0 to 100. That's the antiderivative. To find the answer, the definite integral value, we plug the 100 in, then we put the 0 in, and we subtract, which is done here. Multiplied out, we get 1 million times 4/3, or what is that, 1.333 million cubic feet? That's a lot of cubic feet, but it's a big pyramid. That's the idea. If you have something where you can cross-sectionalize very easily, this is how you set it up. But one of the main ideas in this section is a specific kind of cross-section. It's called the washer method. The idea here is we're going to take a function and we're going to rotate it around an axis. So I'm going to use my hands to describe this. If you take this and you rotate all the way around, you're going to get a circular disc. Now if I take a second one and rotate around, the stuff in between is kind of like a washer. It looks like a mechanical washer, except it may change in shape. It may go faster, it may go slower. The idea is the cross-section is that stuff in there. And the way you find it is you square the outside, you find the area of the outside circle, find the area of the inside circle, and take the difference. So it's pi times the 1 squared minus pi times the other squared. Go from the A to the B, and here's your formula. Now that formula works really well when it's the x-axis. This can also be done on the y-axis. But the trick is, sometimes it's on a different line. So let's just take an example where we're not on an axis. It'll be pretty easy to adjust if we're careful. The idea is still to create the washers, and we'll see how it works. We have one more example here, and pardon the limp. It's my toe, I broke my toe, but my mind isn't broken, so, well, hopefully we're good. Anyway, here is the shape. We're going to take the functions x squared, and we're going to rotate, or instead of around the x-axis, we're going to rotate around x equals minus 1 down here. So the first step is to graph it, to see what's going on. And here's my graph. Hopefully from the graph you can see there's an area in there. That's not actually the area. We don't want the area, we want volume. So imagine this thing is rotating around this this y equals minus 1 line. It's rotating around the y equals minus 1. It creates a kind of a, well, I can't draw it on this board, but it's a shape. That's what we're doing. Then the next step, often you're given these, you often have the A and the B just given to you in the problem. But if you don't, you have to figure where they are. And just like in section 6.1, sometimes we have to solve for those endpoints. The endpoint here is where they intersect. The endpoint here is where they intersect. So we solve where x equals x squared. There's algebra here. Bring the x over, factor, blah, blah, blah. You get A equals 0, B equals 1. Those are important. Those are endpoints. Now we have our endpoints. The idea now is to figure out, just like before, what's the outer radius, what's the inner radius, and do the exact same thing. Well, the outer radius goes from this x line, y equals x, and it goes down to y equals minus 1. So from y equals x to y equals minus 1, it goes an extra 1 distance beyond the x. So we have an outer radius of x plus 1, I'm sorry. The inner one uses x squared instead. So it's x squared, and again, 1 extra. That may seem complicated, but the trick is once you've got that, we just plug them into the formula right here. The volume is integral from a to b, pi times the outer radius squared, minus pi times the inner radius squared. Plug the x plus 1 in, plug the x squared plus 1 in. Make sure you square them carefully, canceling stuff. I've done the algebra right here. If you look over the algebra, it's algebra, and then we integrate it. The idea is going to be that we get 7/15 pi. When you're rotating, pi's are very common. Why? Because you're making circles. Circles use pi. Anyway, that's the idea. Thank you, and next time we'll tackle another topic.